Okay, let's see.
Okay, we're live. Double check.
I'm checking.
Make sure the sound's
Yep, we're
okay.
live.
I think the sound should be okay, but the setup's a little different today.
Okay. Well, people in the chat can let us know if our sound is off. So
Awesome.
let's just get started.
Okay. All right. Hello, everyone. Welcome to today's episode of Quadcast. I am your host, Tim.
Mikey.
And I'm Sahil. Welcome, everybody, to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So without further ado, let's get to it. So I remember last episode, or maybe it was the episode before that, very recently, we were talking about how physics doesn't prove anything. Yet what we're going to discuss is a theorem in physics, which sounds to me like it's synonymous with proof. So I wanted to delve in, like, I guess, do theorems truly exist in physics? Like, what's what's going on with that? Tim, I'm gonna point this to you. You look really eager.
Yeah. So I know, previously in our previous episode, we said that physics can never truly prove anything because physics ultimately is an experimental discipline. Even simple statements like 1 + 1 = 2, you really have to go to the world and measure that. So, but yet there are still theorems in physics, and some of them are quite well known. So it's a fair question to be like, what the heck, what's going on? Uh, so so that and here's how it works. So physical theories at the end of the day are based in mathematics and logic. And if we assume that is true, those mathematics are governed by theorems. So and some of them are have this physical flavor, right? So there are theorems about the mathematics that we use to describe physics, and we use them in constructing theories. But those theorems, nevertheless, they usually don't make they don't prove direct observational facts. Of course, you have to go to the world and measure that. But it doesn't mean that they're useless. Still, they are very helpful to guide us to understand the mathematics behind physics, and that's why theorems are still used to some extent in physics.
I see. You want to add anything to that, Mikey, or
Yeah, I'm trying to think of a simple example, yeah, because it's like as Tim was saying, we did make a point in a previous episode, to talk about how physics doesn't prove anything, and what we really meant by that was, the example we gave is I can drop a ball a million times and it'll go towards the ground. I can't prove that if I drop it a millionth and one time that it'll go towards the ground. Like I can't prove that. I can't guarantee that. Um, Well, as Tim mentioned, the foundations of the language of physics is still based in mathematics, and we argued that math like proof is belongs in the realm of mathematics, not in the realm of physical sciences, because of this fact that I can't prove to you that if I drop a ball tomorrow, it's not going to fall up. Um, so I think the simplest example I can think of is like the transitive property that we all know from like high school, right? Which says that if A equals B and if B equals C, then A equals C, right? That's what the transitive property says. Like if A and B are the same and B and C are the same, then A and C must be the same. And the most important part of that this statement um, for this conversation is the word if. Like if A is true, or if A equals B and if B equals C, then A equals C, right? So in physics, because it's written in the language of mathematics, we can make statements like this. Like if this is true, then this is true. Um, well, I guess my point was in the last episode that you can never prove that the first thing is true. Like, so mathematics can make proofs because it always rests on some kind of assumption. And in mathematics, those assumptions, you can just take them to be true and see what the logical consequences are, and you can prove things. But in physics, we can never take any assumptions to be true. And I think that was kind of the point of the previous episode, is that you can't prove the assumptions. But if you assume the assumptions to be true, then of course you can prove things, because now we're in the realm of mathematics now, not in physics. If you assume that this is true, now we left physics and we're in the realm of mathematics now.
Yeah, I suppose theorems are in physics is kind of the links. It allows you to take these shortcuts that you can jump from one logical statement.
You take these shortcuts through mathematics, right? Like, because physics is written in the language of mathematics, as Tim said, you can sort of use any shortcut in mathematics, you can use it in physics to get an answer easier. That's what you meant, right?
Yeah. And I would say I think in mathematics a lot of times theorems are kind of the goal. Like the goal of mathematics is to prove a lot of theorems on non-obvious statements. But in physics, it's a means to an end. You use the theorems to link your logical statement so that you can make predictions about the world. And some of these links are incredibly important. And in many cases, you cannot do physics without it. So at the end of the day, physics still requires some of these theorems, but more. It just needs more.
Got it, got it. And before we delve into the central piece of this episode of the most consequential theorem, I want to double click onto Mikey, when you were talking about two things being equal to each other, or maybe some other mathematical statement. So I think all of us here agree that you can't establish like true equality, like, oh, this thing is exactly equal to this thing. But what if you said, like, statistically, like within some margin of error, this thing is equal to this thing? So you sort of take a like more statistical or probabilistic version of a proof. So you say like, okay, with some probability, these two things are equal to each other, and you use that as kind of the basis of your theorem. So you say that these assumptions, or I forget, rules, or I'm forgetting the word. It's right off the top of my head. Axioms hold
Axioms.
probabilistically. Yeah. Yeah. So what about going with that approach instead? Does that is that like, does that carry through with physics, or is it deeper than that of like proof in some sense?
I feel like that kind
Because
of
I
opens
know
up
in
a kind of wormholes. I was
mathematics,
just trying to think to myself, like, are there proofs in statistics? And yes, there definitely
well,
are proofs. So, like, typically we think of a proof as like a very concrete statement, right? Like,
mm,
something is, as you said, something equals something. But in statistics, like you said, we're talking about whether something roughly equals something.
mm,
But even in statistics, you can do proofs. Like, there's a central limit theorem which shows that as flip a coin, number of coin flips goes to infinity, the
mm.
probability approaches 50-50. Like, that's a theorem in statistics. So I'll be honest, that question kind of threw me for like, I'm a little confused by this.
Yeah, because
Uh,
I know in number theory they use like probabilistic proofs about like prime numbers and stuff like that, and say, oh, with this probability this theorem holds, or something
Yeah,
akin to that.
I mean, I think the problem is in mathematics, there's an axiomatic definition of probability. And,
Hmm.
in physics, if you assume that's true, sure, you can prove certain things, maybe. But once again, that assumption can just never be validated. Like, how do you know when
Mm.
when things actually don't follow probability, but you assume that it is? And a famous example is probably quantum physics. Like, certain people assume that quantum physics follows certain probability laws, and then lo and behold, when quantum effects are incorporated, everything breaks down, right? And then that's why we have these Nobel prizes. And essentially it comes down to the fact that if you apply brute force regular statistics, you get nonsensical answers. And these are in some sense almost like counterproof by probability. That people have done stuff like that.
Sorry, what are you referring to? Which Nobel Prize are you referring to?
Yeah, I'm
I,
talking
I'm
about
taking Sahil's job here, but
I'm talking about the quantum entanglement bit, right? Like if you assume that if you assume the physical experiment is the same thing as flipping coins, you will not get those results in quantum
Oh, right, yeah,
entanglement. Right.
yeah. So you're
So
talking about the Bell's theorem stuff.
yeah, exactly. The Bell's
Yeah.
theorem and all that, but let's not get into detail. But anyway, the quick answer is that like we just can't prove the assumptions. Like even the assumption that things follow probability is you just have to assume it.
Mhm. So, and then I just want to quickly tie this to d discussion in the past we've had about like we don't have to get into the exact specific details, but in the context of this conversation, like looking at things like black holes, for instance, and using theoretical using theorems and more theoretical understanding to explore like, oh, what should our theory look like? Because you don't have experimental evidence for that. So I'm wondering like is just to frame it in terms of that, like what are your guys' thoughts on that
Yeah, actually, I
overall?
think this kind of relates back to like a previous episodes in kind of an unexpected way. Like, so like we spent a few episodes for those that weren't there, like talking about like what makes a theory simple and what makes a theory powerful. And one of the points we made is that what makes a theory like simple, powerful, elegant, all these adjectives, superlatives, is its ability to um, have very few assumptions while making predictions on a very wide range of things. And
Mhm,
I think, like, yeah, like now that we're talking about it, mathematics, the fact that in mathematics you can prove things is what allows this to happen, right? Like, so like we can take like a physical system, let's say like an electron, right? And then we can write it down using the language of mathematics. If we assume that the electron is a point particle, then I can write down its equation in the language of mathematics. And then I can use the proofs of mathematics to see what else has to be true if my assumptions are true.
mhm,
And this is how physics makes predictions about, far-reaching things that seem to like, you could have a theory of electrons, right? And it might make a prediction about how a gas moves. Like these things seem very far away, but
mhm,
the fact that I can write down the motion of an electron in the language of mathematics allows me to use like the proof type machinery of mathematics to make statements about like now what would happen if I had like a bunch of electrons together in a gas, um, and make statements like that. So really like it's almost like the power of a theory depends on how amenable it is to attack by mathematics.
yeah, yeah. Um, and so actually, there's an audience question that came in that I think is a good time to ask this now. It's a question and a statement. Maybe we can expand upon both to whatever degree you all feel comfortable. So the question is, are you saying that physics does not have any axioms as math has? Relativity talks on space-time and space has three dimensions, and this is a maths concept. The line is an extension of a point, and point is axiomatic in geometry. We assume the point exists.
Yes.
Any
Yeah, I would say that's exactly right.
thoughts?
Yeah, like that's yeah. In math, we have axioms, and math is about seeing what is the consequences of those axioms combined with a set of logical rules, right? That's what math is. In physics, we don't have axioms. Every axiom must be questioned. We can play this game where we can pretend to be mathematicians and take axioms, and then we can see what the consequences of these axioms are, and see if and then use experiments to check to see if it holds up in the real world, and then we can use it to say, okay, this axiom is good, this assumption is good, or this assumption is garbage.
Yeah.
Um,
And
and yeah, that's really the difference, I think. I
I,
think that question hit the nail on the head.
I think I'll go for a little further than that. I would say a large part of physics, the goal is to nail down which axioms to assume, and that's the thing. You have some axioms, you make some predictions from those axioms, and then hopefully that gives you evidence that some of those axioms are true. And of course,
Yeah.
if that's wrong, then you know your axioms are wrong. Like in math, the axioms are sort of the starting point, and in physics, I would say the axioms are the end goal.
Yeah. Like which assumptions are good assumptions and which assumptions are bad assumptions. Like I said, like we're always like the goal of physics is to constantly question and refine your assumptions. And yeah, that's essentially why proofs have no place in.
Yep.
They have a place in physics in the development of the theories, but they don't have any place in terms of applicability to experiments.
Mhm. What? So now, one question that came to mind is when we mention the word axioms, I think of piano axioms, but we don't need to delve too deep
Piano?
into that. But essentially, the existence of like numbers themselves, like counting one, two, three, four, five, all the way on. Is there any case in physics where that's just like broken? That axiom itself, that integer numbers exist, just doesn't hold.
People have
It's
questioned
like
that.
so basic.
People have questions. People have tried to come up with theories that even make, you know, because one of the crux of having a number system is how far away numbers are. Some people might have
Mm,
questioned that. Maybe at very large energy, somehow that those statements are linked to very small energy. So the distance between 10,000 and 1 might not be 10,000 minus 1. So some people have come up with modification to that, and they have delved into different, like algebraic geometry and stuff like that. Of course, a lot of them are not mainstream, but yeah, even the most basic assumption people have questioned, and it's part of the game in physics.
Yeah, the more basic of an assumption you overturn, the more famous you become.
If it
So
turns out to be true.
yeah, there's a lot of motivation in the field for people to constantly question and
Yeah.
overturn assumptions. I mean, well, yeah, I don't want to say that. Now we're getting into the thing that we rage against, where we're like, oh, Einstein was proven wrong. Yeah, I mean, there's such a strong incentive for scientists to try to do that. Yeah, but
yeah, but I assume it carries a lot of risk if
yeah, it's not
you
always a
keep
good thing.
making theory.
That's for sure.
Yeah. So yeah, I want to ask you guys point blank, what do you think is the most consequential theorem in all of
Oh,
physics?
Noether's theorem.
Yes.
Noether's theorem.
well,
Ah,
first,
I got the right answer.
I think we need to go through a few different candidates, at least the ones we know. And the audience might not know this, but at least
Wait. Hold on. Let's just do a quick refresh of what exactly we're categorizing. We're categorizing what the most impactful, um, the most far-reaching like mathematical statements in physics, or i.e. proofs or theorems in
mhm.
physics.
Yeah,
Yeah.
I mean, yeah, what you said.
What are the ones? What are the typical ones? Things that people think about? Because I think the goal of this episode is to get people to understand that Noether's theorem is the most powerful and far-reaching theorem in physics, and no one's ever heard of it, which is crazy. But like, so what would the typical person say? Like, what is the most, like the theory of gravity, right? Probably, or
is that
something
What
like
about
would
like
that
that.
even
quantum
be a
mechanics?
yeah?
Yeah, quantum mechanics.
Would those even be theorems? They're more like theories, but I guess
Yeah, but I think you can still
Wait,
say that Noether's theorem, like even though it's like apples and oranges in a way, Noether's theorem is still like you can still say it's a much bigger statement than any because Noether's theorem applies to all those. It applies to classical
mhm.
mechanics, quantum. It kind of like subverts all of these disciplines and
So
makes powerful statements about everything uniformly.
hmm. Maybe it might be helpful because when I think of the most consequential theorems, I think of like things that are in like general relativity, reformulates the whole space-time, quantum mechanics, and then I guess like even going way back to like classical mechanics, Newton's laws and stuff like that. But yeah, maybe it might be helpful to distinguish like are those things theorems? What are we calling theorems? Are theories made up of theorems? Like, just want to really understand the taxonomy here.
I mean, I think
Cool.
it's a little difficult. I mean, in some sense,
Mm,
you probably on some level you could call Einstein's theory of gravity a theorem, right? Like it is a mathematical statement. Um,
mm.
but I would say it's
No,
a little.
no. Would you call it a theorem? Would you call it an axiom? Like, wouldn't it be an assumption that Einstein's theory is true? And then you would say, okay,
Well,
well, if Einstein's theory is true, then a corollary of that is you should see like some precession in the orbit of Mercury, for example,
right,
right?
right. But I would say there are some statements in Einstein's theory that are kind of in the form of a theorem, right? Like it's like if you assume Einstein's equation is true, then like you add this term in it, and this will cause this effect, right?
Sure.
Like if
Yeah.
Einstein's theory is true, that matter will create curvature. You can kind of say that. Like
Mhm.
Do you think F equals ma is a theorem?
yeah, like
That's what I was asking myself.
I'm not saying it should be, but
Seems like a
I
definition.
can see that on some level it could be viewed as derived from something else. But 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 I think that generally people don't think of them as theorems because they're a little too specific, isn't it? They're a little too
Well, I
specific.
mean, if we're rating theorems, like I would say that being specific is a weakness. So let's be generous and say that like Newton's theory is a theorem. Like if a particle has a mass of this and an acceleration of this, then it will exert. Like you can do it if then, right? So okay, we can phrase it as a theorem,
Yeah.
right? But it only applies to hard marbles. It doesn't apply to anything else.
Well,
So
hard idealized marbles, right? So it's kind of
yeah,
lame, basically, like theoretical
yeah, it really
marbles.
just applies to a very like it doesn't it's garbage at describing atoms. It's garbage at describing planetary motion. So yeah, it's that Newton's theorem uh, is whack.
Yeah, and also I guess there are other candidates, right? Like you can argue laws of thermodynamics, like the fact that entropy goes up. You can kind of think of it as a theorem. Like if a system exhibit chaotic behavior, you can show that. I guess you can kind of mathematically prove that entropy goes up, and that you can argue that it applies kind of generally to many systems. But I would still say that this sort of theorem is not as powerful because it's kind of
Yeah, definitely not.
an approximate statement, and it also has and also the statement the entropy goes up isn't that powerful. Like I know it is powerful, but like it doesn't tell you a whole
Yeah,
lot.
we're talking about relative power here, right? Like,
Yeah,
it's next to Noether's theorem, it seems like it's not that powerful because Noether's theorem is so powerful. I think this is the best way to describe how powerful Noether's theorem is. Just to talk about like what is it like? Okay, so I guess this is one thing that you have to believe. So I have to try to convince you of this, is that all of physics, all of our understanding, and all of the sense we can make from this world depends on the fact that certain physical quantities are conserved. I hope I didn't get too technical there, but like, hopefully people know that energy is conserved, right? Or, well, at least approximately, energy is conserved, momentum is conserved. You have these
Momentum.
quantities that are conserved, that are the same at one point in time as they are to the next point in time. Um, can you imagine how hard it would be to do physics if there were no such thing as a conserved quantity? Like, imagine that there was no rule that said the energy today has to be the same as the energy tomorrow in this box if I don't let anything out of it. If the energy is allowed to just, if it doesn't have to be the same, if it's allowed to be anything, then there is no physics, right? Like, all of physics depends on the fact that there are certain things that stay the same from one moment in time to the next. If you don't allow me to take advantage of that, then I can't do anything, right? I don't know. Agree or disagree, so
Are you asking me or are you asking Tim?
yeah, asking you. Yeah, I'm
Oh,
wondering if
asking
that's
me?
convincing because it sounds.
Uh,
I feel like it's a little hard to convince people that the existence of conserved quantities in nature is so crucial to our understanding of the universe. But I just feel like try to imagine what the universe would be like if energy was not conserved or if momentum was not conserved. Like you'd have particles just
yeah.
I
like
mean,
there'd be no predicting anything.
I don't really have to imagine. I mean, that I do believe that's already happening as you like go to grander and grander scales. I sense that physics is kind of breaking down because you're losing these conservation laws like one at a time, and now it seems like there's only one left. But now
Well, sure. Yeah,
even
well, when
that's
you go
being
to
called
grand
into
scales,
question.
it's true you do lose the conservation, but at least they were there to begin with. Can you
Mm.
imagine if they were never there to
Yeah.
begin with at all? Then, like, where would
Yeah.
we even start?
Oh,
Like, there'd be
yeah.
no
I don't even
order
know.
to. So, our ability to understand the universe, I think, rests crucially in the fact. that our universe keeps things constant, keeps certain things constant from one moment in time to the next.
Yeah.
That
Would
is
you
like
say,
the most important fact about the universe,
would,
that it does keep things constant from one time to the next.
would you say a good analogy is kind of like inflation? Like imagine that the price of eggs is going like it's triple the tomorrow and like half the next day. Like no one would be buying groceries anymore.
No, no, no,
But
no.
it's
It's deeper than that. Like the monetary analogy would be like, okay, like we trust money because we believe the money is tied to some form of value. But if you're telling me that money is not tied to anything and it's just some random number, then yeah, how can I make any sense of value? Yeah, I think
yeah.
that would be the analogy.
Well, I guess so far we haven't talk about what Noether theorem is yet. But
Well, no, I'm just trying to establish. Well, Noether theorem is about conserved quantities, and so I was just trying to convince the viewer that conserved quantities are actually the linchpin, like that underlies our ability to do physics. And that's why Noether's theorem is so important because it
Mhm.
tells us what to do with this information. And if we don't have this information, we're dead in the water. I'm not sure if that was
Mm.
convincing or
So
not.
I mean, it's convincing to me at least that you
Mm.
do need conservation laws, and so I guess Noether's theorem discusses conservation laws, but like, I mean, do I really need a theorem for that? Like, I just say, oh, energy
Oh
at like this
yeah,
time is equal to this time.
yeah.
Like, why do I need a theorem for that? Like, it's
yeah,
just
No, no, no. Well,
what you said.
so now we haven't gotten to what another theorem says. Yeah. You do need a theorem for that, and it's a very useful theorem because Noether's theorem basically gives you a recipe um for like if you see a conserved quantity, you know how to write down the theory with that conserved.
Mm,
It's basically a recipe or how to observe a conserved quantity and then immediately write down a theory that describes it, like without even doing any thinking. Um,
mm.
so yeah, it's like having like a superpower, like a godlike.
I guess Tim, what are your thoughts on this? Like,
yeah. I think some historical context is probably useful, right? Like I think back in the days,
mhm,
people try to describe imagine your job as a physicist. You're trying to describe system, and let's say you observe a ball moving left and right, and you're like, well, why does it move? Why does a ball roll down an inclined plane, or why does a block move on ice, right? And then you try to come up with these equations, and it's tough work, like you got to be creative and kind of write down these equations that describes the system, and it's just like throwing a dart in the dark, right? Like you need kind of some knowledge. It's like a black art, you need to have some knowledge on roughly how do these equations work. But people notice that in all of these systems, there is what we call conserved quantity. Let's say energy is conserved, right? But then it turns out that, and then it gives you a little bit of a hint. Now, if you're not very smart, maybe you would try to write down equations in such a way that
mhm,
energy is conserved. But the job is still pretty damn hard, right? I can write down millions and millions of equations. And, what's the chance that, you know, sometimes the energy will be conserved, right? But what's powerful is Noether's theorem tells you that if you have something called symmetry, like basically a theoretical principle, a theoretical construct, you can immediately say that your system will have conserved quantities. It basically translates an observational fact um, into a theoretical construct. Um, and that's what makes it
mhm,
powerful. It provides a guidelines. So the moment you say, "Hey, look, look, this quantity looks like it's conserved. Energy looks like it's not changing," or some other random numbers that you're doing experiments with. It looks like, hey, it's not changing no matter what I do to the system. Then the amount of possibilities in the theories that you might construct immediately shrunk. I mean, like be like, hey, look,
mhm.
this is this is now my job as a physicist becomes easier. Like I know where to look. So it's very powerful.
Mm. Can we give some examples of like symmetries and what conserved quantities they tie to, and maybe some intuition around that? So for instance, like energy conservation, what is that? What symmetry does that imply, for instance?
Energy is hard. So space is easier. Let's
Oh,
start with
then do do
space.
do a different one. Do whichever one you feel comfortable doing.
Ah, I
So
think
so let's just say like just straight up what Noether's theorem says. Like this, like just like it's very simple to say what Noether's theorem says.
Hmm.
Noether's theorem says that if you have a theory, let's say like okay, it's very abstract. I apologize for the abstractness, but if you have a theory of nature, let's say just abstractly, like you can pick any theory you want, like Newton's laws or general relativity, whatever, just whatever you have. If you have a theory of nature, or whatever you think it is, if this theory has the property that I can bend it in some way without changing the predictions, um, then there must be a conserved quantity in that theory. And Noether's theorem gives you an exact recipe for how to take that
Hmm.
bend of the theory, this bend, like, so I'm taking a theory and I'm bending it. So you don't know what bend means yet. But I can take a theory and I can change it in some way without changing the predictions. Then Noether's theorem gives you an exact recipe for how to take that change in the theory that did not affect your predictions, and then immediately calculate which quantity is conserved. So you can do this with a bunch of different things. The most basic thing you can do is take your theory, and the most basic way to bend it is just by moving it like a spatial translation. Just move it like 10 meters to the right, let's say, or 10 meters
Hmm.
forward, 10 meters to the right, 10 meters left, right? Um, Most physics theories, or yeah, I guess you could say all fundamental physics theories, have the property that if I take the theory and if I just shift it over by 5 feet, it's the same theory, right? Um,
Hmm.
like if I have like a gravitating body here and I just move over here, it's not going to change the way these two bodies are gravitating, right? The physics is the same even if I move over in space.
Hmm.
So that's one way to bend your theory or to deform your theory or to change your theory, right? And that's one way to change your theory in a way that doesn't change the physics, right? If I take the whole theory of the universe and I just shift it over by 5 feet, we wouldn't expect any of the predictions to change. And it turns out if you apply Noether's theorem to this particular change or deformation or bend or whatever, you get conservation of momentum. And it gives you exactly conservation of momentum. And it's very, very clear that this, um, we call an invariance in the predictions with respect
yeah
to a change in the theory, gives you some conserved quantity like momentum or energy
yeah
or charge or anything that's conserved.
yeah. And I would say if you just think about that statement, it's actually somewhat intuitive. What is the conservation momentum? It tells you that an object that's already moving to the left, let's say, will keep moving to the left unless something happens to it. It has a tendency to move to the left. It has a momentum moving to the left. And how is that linked to symmetry? The theory tells you that, hey, if you have a theory that doesn't care about where things are, then it makes sense that if something is moving from the left to the right, because the same theory is going on at every location, it can't possibly all of a sudden care about that it's moving left to the right. And sort of, I guess there's sort of a little bit of the intuitive link. The fact that the theory doesn't care about where you are, that means there's some kind of currency to keeping track of. Hey, um, to keep track of this value, where you are is not changing, and that translates to momentum. And it turns out that this analogy kind of can be applied over and over and over again into things like energy, angular momentum, charges, and even crazier stuff that people have never thought of might be related to symmetries. Um, so
Seriously, what the hell does conservation of energy have to do with conservation of charge? It doesn't seem like they're related at all. Noether's theorem tells you that it's one recipe and you derive both of those things. It's crazy. It's It just links everything.
Yeah, actually, I want to challenge this a little bit in terms of the analogy. Like, I guess like intuitively, I understand what you're saying about if you translate a system over that has momentum. But couldn't you say the same thing about charge? Like, as you know, if you move something over, the charge will still be the same, or the energy will still be the same. So I guess like, wh why is it specific to momentum? Is there any intuitive understanding about that in particular?
I think the thing that makes it intuitive in Tim's explanation is that because momentum is about your motion through space. So if you're
Hmm.
saying that the theory doesn't care about your where you are in the space, then yeah. Where it's like I guess it's harder to draw the
Yeah,
analogy with
I
charge.
mean,
But I wouldn't care about charge if I move the system over. The charge remains exactly the same.
that's the beauty. If your theory doesn't care about your charge, it likely means that actually you have a symmetry. There's a symmetry in which the charge it doesn't care about the charge. I mean, I think it'll be nice. It would be nice to get a counter example, right? Like, how do you destroy the conservation of momentum? Like, for example, you can put a wall right here. Imagine the universe as a
Yeah.
wall. You move and you cannot pass it, so you just move and you hit it. And of course, any particle that moves eventually will hit it, and then they will stop moving. And all of a sudden, momentum is not conserved now because there's a wall, and you just had a dead on
Wait, sorry, just to
collision.
clear, yeah. So like the wall means that now the laws of physics here are not the same as the laws of physics over here,
Right.
because one is
Yeah.
in the wall and one is outside the wall.
So,
So like
mm,
one way you can
Mhm.
break conservation of momentum, as Tim mentioned, yeah, is to put a wall up. And now I've broken this symmetry. This now when I bend the theory and move it 5 feet to the right, it does affect things because there's a wall there. So and then you see non-conservation of momentum.
Mhm. But if you view the particle on the wall as like one part of the system, I mean, momentum technically should still be conserved because if you, no matter which way you move it, then it'll be the same, right? Should I think of it like
if
that?
the wall itself is movable, then you can
Yeah.
take into account the momentum of the wall. But
Hmm.
then that means your physics doesn't care about where you are anymore. But it's just that it's a theory
Mm.
of
Yeah.
particles and
And
the
then if you look at
wall.
the whole wall thing system, then on the whole system momentum is conserved.
Right. But
I see. I see.
it's not totally ruled out that maybe the universe has an impenetrable wall. I mean, we don't think it's true, but like,
Hey,
it,
domain law theories are still pretty hot, right?
yeah, like you could, yeah, but probably most people wouldn't think that there's a hard wall that's fundamentally impenetrable. Then yeah, that will
Yeah, but there's
violate.
fun games you can play with with
Yeah,
such ideas.
Hmm. So I guess can we ask sort of the converse question? So I guess Noether's theorem, does it state that which direction does it state? Does it state that if there's a symmetry, then there's a conserved quantity, or if there's a conserved quantity, there's a symmetry?
The first
Which
one.
direction? The
yeah,
first one. What about the other way? That if
That's a
there
question for
exists a
Tim.
symmetry, does there imply that there's a conserved quantity?
yeah. I think generally Noether's theorem goes one way, and in some limited
Hmm.
cases, you can kind of show it the other way is true. But this
Hmm.
is sort of where magic happens, I would say. And I can't think of a counter example, but whenever physicists found conserved quantities, you should always ask the question, is there a hidden symmetry? And this is kind of a bit of an art. I don't think you can always construct it. And this is sort of the job of a physicist. Like I think physicists in general believe some sort of converse is true, but I don't think the other direction has been proved um, definitively. I don't think so. But then this is why sometimes physicists find surprises when you discover certain things that doesn't seem like it's a conserved charge. That's associated with a symmetry turns out to be true. Like for example, like the electric charge, for example, right before Noether's theorem, you wouldn't think that's associated with any symmetry. You know, like all like in some sense, all the symmetries, like back in the days, all the symmetries have been accounted for, right? Like the
Hmm.
movement of objects and rotations is linked to conservation of energy, momentum, and angular momentum. What's up with
Hmm.
charge? And not everything has a charge. So clearly, we are not talking about we're not talking about transformation in this way. Like it's got to be a transformation that applies to a selected number of particles. But it turns out
Hmm.
that once you go into something closer to the quantum physics realm, people figured out that hey, the charge conservation is actually linked to what we call an internal symmetry, and a symmetry that's invisible. And there's this abstract rotation in an internal space that you can kind of maybe visualize. Like imagine the space is a little circle everywhere, and you sort of move in that circle, right? And that physics is the same where no matter where you are on that circle. It turns out that abstract symmetry in this little tiny circle that only certain particles can move through lead to the conservation of charge. And that's why like some of these surprises are not obvious.
Hmm. Get two questions for you. One you can answer super briefly is what's the theoretical name of this internal symmetry, just for my curiosity?
It's I think we can call that the gauge symmetry, right? I think that's fair.
Yeah.
Oh, okay,
Yeah.
Yeah,
okay,
it's the gauge symmetry.
okay.
Yeah,
And then
mhm.
mm. and then my next question is like, okay, you discover these internal symmetries, but you can't, they're not observable. Why are they useful? Like what can you do with this that is actually giving you like something that's useful?
Oh, here's something that's not useful but still cool. Like literally, like what Tim said is like if you take a smooth space and if you imagine that at each point in that space there's a tiny circle and only some particles can move in that circle, you get electromagnetism perfectly. Like it works, you get Maxwell's equations out of that. So it's cool that you can just take this very simple assumption. You imagine that we're just all moving through the smooth space, and you just imagine that there's a tiny circle at each point that some particles can move in that circle and some can't.
Mhm.
You get Maxwell's equations. So it's almost like a simpler way to derive all that we know.
Yeah.
Mhm.
Yeah. I mean, and it's just hard to even think about how far people have taken this idea. Like you said, electromagnetism. People nowadays think of it as pretty trivial, right? But you can take that one step further. Instead of having a little circle, what if you have a little sphere? Well, lo and behold, if you have something like a sphere with some technical details, you actually get the electroweak force. Like, and if you generalize that sphere to a more complicated object, like a complex six-dimensional complex sphere, I don't even know how to visualize it. You get the strong force. You just get it, right? Um, and then physicists have also found like some much crazier examples of these like symmetries that are just have no business of being symmetry. Like no one ever thought of that it looks like a symmetry, but it turns out it is.
Mhm.
And we even have these very much more generalized notions of what symmetries are, and it's just I would say people are still pushing the boundaries of this Noether theorem.
Mm. And what about for like, I don't know if you want to call them conserved quantities, but they are conserved like I guess in particle interactions, they make up these different numbers like lepton number, baryon number. They give these numbers to like this particle has this particle has this number, and this like quantity that we just made up is conserved amongst all these like different things. Is there a symmetry associated with that?
So I would say that the symmetry game is a little difficult, right? Sometimes,
Mm,
like for example, lepton number, only for those who don't know, lepton's number are numbers that only account that only applies to particles like electrons, muons, taus, and neutrinos, but nothing else. So in some sense, they're a little bit rare because there's only very few candidates particles that
mm,
that that, that they apply to.
mm,
So you might think that in everyday experience, it seems like it's conserved because you can't just destroy an electron out of thin air. But we
mm,
don't know quite yet ultimately whether this is truly conserved quantity. right?
Mhm.
But then if you do believe that it's a conserved quantity, then it's true that then you should believe there's a faithful symmetry governing it. But actually, I think there are complicated processes that could violate, um, at least theoretical processes that could destroy it. So lepton number is probably not the
Mhm.
best symmetry, but they are.
No, but the fact is we observe it. I think like yeah, I think we're getting away from the point, which is the fact that we observe lepton energy, like maybe just at low energies, whatever, that's fine. And then we write down a theory, and to answer your question, yes, indeed, the theory does have a symmetry. There's lepton
Mhm.
numbers that you won't like. It's like when you're building a theory, you know from observations that lepton number has to be conserved at least at low energies. And
Mhm.
Noether's theorem, if you understand Noether's theorem, then that tells you what kind of theory that you need to build to have
Mm.
lepton number conserved. Um, so yeah, it's really just a recipe.
I see. So if I one day like I don't know comb through all the data and I'm like, oh, I'm just gonna make up this like conserved quantity, and let's say it's legitimate,
Oh, people
it
do that all
holds
the
in all the
time.
cases
Yeah,
you've seen.
yeah. Making up conserved
Then
quantities is
like
like a cottage industry.
I see. But if there's like one case where it doesn't hold, then can I say in that case the symmetry is broken, but in all the other cases the symmetry holds?
Um,
Does it work
like
that
there would
way
have to
or
be some
not?
like
Not
like
really.
you could say like, oh, when I raise the temperature, the symmetry holds, and when I lower the temperature, it
Yeah,
breaks. But if you just say you would
yeah,
have to
something
have
like that.
some logical rules for when it applies and when it doesn't, and then I would say
I
it's a
see.
viable candidate.
Got it, got it. So, we have an audience question that is, can you give an example of bending a theory? What exactly do you mean by this?
Yeah,
Question
oh
for you,
yeah. Well,
Mikey.
the first example I gave was just the one way to bend a theory is just to like take the theory and move it five feet to the right. And that way of bending a theory, just shifting it five feet to the right, that way of bending a theory is what gives rise to conservation of momentum. Another way you can bend the theory that we mentioned is by putting a circle at each point in space, and you can say the theory doesn't care about where you are in the circle. Everywhere in the
Mhm.
circle is okay. So you're basically taking the theory and you're saying, okay, I can twist the theory around in circles and I get the same predictions.
Mhm.
Well, if you write a theory down like that, you automatically get something called electric charge that is conserved in every interaction. So
Mhm.
yeah, bending the theory, I agree. I apologize. It's a very abstract description, but I mean things like moving the like taking a theory and literally just shifting it 5 feet to the right, or taking a theory and just bending it in the time. And what are the different ways you can bend a theory? That is exactly the art of theoretical physics, is finding new ways to bend theories that people haven't thought of before.
Got it, got it. So we're almost at time. So I want to give you guys a chance in our usual tradition to leave the audience with any words of wisdom that Noether's theorem has taught you, and maybe like some summarization of like the highlights of what we've talked about, because we covered a lot with this theorem.
It's kind of hard because it's so far reaching. I think that like it's just crazy. To me, it was crazy. Like, once I fully understood Noether's theorem, the fact that no undergraduate student knows what it's great. Like you could say that every single Nobel Prize after 1950 is directly like Emmy Noether deserves all of them. Like every Nobel Prize after 1950. Like,
But she never got one. She never
it's
got
like
one,
that.
unfortunately.
Huh?
Noether never got a Nobel Prize, right? Which is kind of absurd.
Yeah, yeah. It's crazy. It's like people are like, oh, like should special relativity have gotten a Nobel Prize? Like, and it's fine because Einstein already got his credit, but like Noether's theorem is a way, way more egregious example than that.
Yeah, and I would say personally, if you look at the trajectory of physics, it seems like a lot of theories, like Newton's theory, Einstein's theory in quantum physics, ultimately they're not 100% correct, right? Uh, eventually theories get superseded by better theories. But in some sense, you can argue that theorems are infallible because they are mathematical statements, right? As long as the assumptions are valid, their conclusions are valid. So if you take that lens, then you can argue in some ways that theorems are more powerful than physics in that way, and because of that, like Noether's theorem it's timeless in some sense. Like it'll probably never go away. Like the concept of
Hmm.
linking symmetries to conserve quantum physical results will probably always be there. It doesn't matter how our theories change, right? I probably will bet money on it that concept would never go away. So I guess in terms of like theory immortality, that's probably that and I guess you can argue that I don't know, Mikey. Like philosophically, would you say that this theorem, even though it's a mathematical statement, it feels like it tells you something greater about the universe?
Oh
I don't
yeah,
know.
more than any other theorem. I think that's really what makes it special, right? Is like it. I can't prove that this is true, but as Tim said, like when you're just like it's like looking at a mountain that's like huge and just being in awe of like it's you get that feeling when you look at another theorem.
Wow. Before we end the episode, one question I have for my own curiosity is in special relativity, there's Lorentz symmetry, the symmetry between space and time. What conserved quantity does that apply to, or do you get from that?
We do. The boost actually.
Oh yeah, what is the boost? Oh, that
The
one's a weird one, and you never hear the answer to that question.
there is one. It turns out the boost is a time-dependent charge, which is a little funky.
Yeah, that one's really weird.
I forgot exactly how it works, but it does work. But people don't talk about it, of course. But I think it is there.
No, definitely there. Yeah,
There are other weird ones, like if your theory is a fractal.
like the wrong lens vector.
Well, that's different. That's different. And also if your theory is like a fractal, which is a symmetry, if you zoom in and zoom out, it looks the same. There is a conformal charge that is conserved. Um, I don't exactly remember what that's like, but it tells you. I don't know. There's some really unintuitive ones, but I think mostly because we don't really use it, but maybe
Mhm.
yeah. I'm not sure what to tell you, but there's some really weird charges that exist, and they may be more useful than you think, but we don't talk about them.
Yeah. So, yeah, I think that's a great place for us to end. So on that note, I want to thank you